So, hi everyone, good afternoon. Okay, so welcome back to our class in linear algebra. So, our topic today is Eigen analysis, yeah, Eigen vector and Eigen values. Okay, so I will share my screen. Can you see? Okay. So we will discuss a lot of topics, but this is in the same group of topic. Yeah, it's called eigenvalue, eigenvector. Okay, and I want to show you the relationship between these two trace and determinant, and then we will develop the modal matrix. And one of the application is to create the diagonalization. Okay. In fact, say if you want to use difference equation, okay, and then you want to know the stability, you need to know the eigenvalues. Last time I demonstrated to you about PCA, you remember? Principal component analysis, that computation is also based on eigenvalues. Last time also I introduced to you about singular value decomposition, SVD. Okay, these are also based on eigenvalues and eigenvectors. Okay, in fact, those are the modal matrix. Okay, so let's go to the formalization. So look at this form here. If you have a matrix, okay, if you have a matrix A, okay, and then you multiply by a vector V, okay, and then if this matrix multiplied by this vector V is equal to a scalar lambda multiplied by the same vector V, okay, what can you think about this lambda? What can you think about this lambda? Hmm? So you have a matrix A, okay, and I can find a vector V. Then if I multiply this A with V, that is exactly the same as lambda, which is a scalar, say for example 1, 2, 3, and so on, multiplied by the same vector V. What will happen? That means A is the same as lambda, isn't it?
Yes.
Yes. Right? So A is the same as lambda. So that means one whole matrix, regardless the size, okay, 3 by 3, 5 by 5, 100 by 100, I can characterize that matrix by one number, lambda. Awesome. What is that number? Okay, so that number is called eigenvalues. Eigen means true. Okay, so that means eigenvalues is the true value of that matrix. That one numbers represent the entire matrix. So that's awesome. Okay, but that will not happen to any vector. Yeah, this always happen only at certain vector V in here. So this called eigenvector. So eigenvalues must be accompanied by eigenvector, okay, in order to make the matrix A can be represented by a number. Is it clear or not, the concept of eigenvalue, eigenvector? Okay, so remember, matrix times vector is practically a transformation of vector, isn't it? Now I have, if we can find the number lambda, so that transformation of vector is just a scaling of vector, isn't it? Lambda here is just a number, real number, or complex number. Okay, that if I multiply this by that vector, okay, that now the vector is just scaling, yeah, shorten or lengthen or reverse direction. Yeah. Lambda can be a negative, so reverse direction. So in that case, the whole matrix, yeah, can be represented by a simple number. Okay, so given a square matrix, A must be a square matrix, we can always find eigenvector V, yeah, so that when if E is transformed by A, it will multiply by itself. Yeah? So that's the meaning, right? The meaning of this is scalar multiple, yeah. So eigenvalue is a scalar, so that means this is a scalar multiple of eigenvector. Okay. So for example, I give you example of matrix A, 5, 4, 1, 2, yeah. Okay. And then I can find the eigenvector. So I will show you later how to find this eigenvector eigenvalue. Okay. So I can find this eigenvector 4, 1. So if we multiply, okay, 5 times 4 plus 4 times 1, right? So 24. And then 1 times 4 plus 2 times 1, so it becomes 6. Yeah, this is exactly the same as 6 multiplied by the same vector. Can you see this is exactly the same vector? So this is actually the eigenvalue, and these are the eigenvector. Is it clear or not?
Understand.
Clear, yeah? So I can find, okay, from any matrix, okay, eigenvector and eigenvalue. Okay. How to calculate? A little bit long to calculate, but you can find. As long as A is square matrix. This is another, the same matrix, okay? I can find another eigenvector and eigenvalues. Okay. In fact, if you have 2 by 2 matrix, you will have 2 eigenvector and 2 eigenvalues. If you have 3 by 3, you will have 3 eigenvectors and 3 eigenvalues, and so on. If you have 100 by 100, you will have 100 eigenvalues and 100 eigenvectors. Okay. So you see, if I multiply, yeah, you see, yeah, 5, 4, 1, 2. So 5 times 1 plus 4 multiplied by minus 1, you will get 1. Right? And here, 1 times 1, and then plus 2 multiplied by minus 1, so we get minus 1. Yeah. So this is the same as, this is exactly the same vector, right? Can you see? So that means this is the eigenvalue, and this is the eigenvector. Yeah. See, yeah? Okay, so geometrically, we'll say operation of A on this vector V is only change the length, yeah, perhaps the size. It never rotate to other point. It's just stretch or shortens or reverse direction. Okay, so remember, matrix A can do anything, can be reflection, can be last time your assignment, yeah, can be reflection, can be shear, right? Can be rotate, yeah, can be translate and so on. But this one, look at this, using eigenvalue and eigenvector, you can only scale. Yeah, you don't rotate, you don't shear and so on. Only change the length. Okay, only one transformation using this. So, okay, now how to compute? How to get the eigenvalue and eigenvector? Yeah. So we go to the definition. You see, can you see here? I have AV equal to lambda times V, right? So in that case, I will put this right hand side into the left hand side. Yeah, I will put it in that side. Okay, so that means A minus lambda. This is V and V, right? So I can put it out. Okay, so lambda times I, yeah? Because you cannot make subtraction unless you use the same matrix. So I times lambda is just a diagonal element, okay, is the same as lambda. Okay, And then, of course, now you can put it in the left-hand side. That means right-hand side becomes 0. Okay, so this will have solution. Remember, homogeneous equation, right? So this will have solution if and only if this determinant is 0. Yeah. So that means you calculate A minus lambda times I. So, and then you calculate the determinant. Yeah. So this determinant will become polynomial. Yeah. Be careful, this polynomial can be complex or real. Okay. So eigenvalue not necessarily real number, can be complex number. Okay. So even if A is real, okay, eigenvalue can be complex number. Yeah. So, okay, let's me summarize. Yeah. So given a square matrix A, okay, then you can form what is called characteristic equation. So characteristic equation is you form A, okay, minus with lambda I, and then you get the determinant and then equate it to 0. Okay. And then you find the root equation. Yeah. That root of equation become eigenvalues. Okay. Once you get the eigenvalues, you put it back. Yeah. You put it back to solve this equation. You will get the eigenvector. Yeah. These are the steps. Up to here, is it clear or not? I will give you example in a few moments, but can you remember the steps?
Sir, question, sir.
Yeah, cool.
In the previous example,
Mm-hmm. This one?
yes, this one. I still don't understand where you get 6, sir. 641.
Look at this. I have V, this one, right? And this one
Mm-hmm.
also V.
Mm-hmm.
Correct, yeah?
Yes.
So
Yes.
now 6 times 4 is 24.
Yes.
Times 1 is 6.
Oh, okay.
Okay, so if you don't know this, okay,
Mm-hmm.
so this one is actually 24, 6, right? Multiply. 5 times 4 plus 4 times 1 is 24.
Yes.
And then
Oh.
1 times 4 plus 2 times 1, 6.
Mm.
Okay, now I put it out. 24 and 6, I put it out 6 in here. So this one become 4 and this is become 1, which is exactly the same as this one. Correct or not?
Okay. Okay, sir.
Clear, yeah?
Clear, sir. Thank you, sir.
Yeah, yeah. So anything else? Go ahead. If you have any question, don't hesitate to ask. Yeah? So the steps of computing, is it clear or not? Okay, let me give you an example of this a while ago. Okay, how to get that 6 and 1 now. Okay, I used exactly the same matrix, yeah, 5, 4, 1, 2. Okay, so what you will do, you have A, so what you will do is A minus lambda I, isn't it? And then you get the determinant. Yeah. So we create the characteristic equation. So A minus lambda I. You see, A, oh, is it clear? A is 5. I is what is I? You remember? 1, 0, 0, 1. Yeah, this is I. Okay. So I equal this one, right? Identity.
Is I the identity matrix, sir?
Correct. I is the identity matrix. Okay.
Okay.
So so lambda times I, so that means U minus, so 5 minus lambda. This one is 2 minus lambda. Is that okay or not? So can you solve this? Okay.
Lambda equals 6 and 1.
Correct. Correct. Very good. So
Super.
super. See, lambda equals 6 and 1. Yeah. And then from there, from lambda 6, can you solve this? Can you solve this one? Okay. Can you try to solve? So you put lambda 1 equal to 6. Okay. So you put it A minus 6 times I. Okay. You want to find V1. Okay. So remember A is 5, 2. So now we know lambda 1 is 6. That means you minus with 6. Yeah. Okay. We don't know V1, V2. That's okay. Yeah. So then 5 minus 6 is minus 1, isn't it? 2 minus 6 is minus 4. So up to here, is it clear or not? Okay, so now we want to solve this. So how to solve this? This is homogeneous equation. I hope you know how to solve.
Is it the same, sir, like 4 divided by minus 1?
This one means minus 1 times V plus 4 times V2 equals 0.
Oh, okay.
Okay? And then V1 minus 4 V2 equals 0. So, okay, so then you will get right. So we have minus V1 plus 4 V2 equals 0, right? That means what you have. So this is the first equation. The second equation is V1, okay, minus 4 V2 equals 0. Okay? So can we say that V1 equal to 4 V2, right? Because this is actually a line equation, that means you can put any value of V1, isn't it? So I can put, for example, I can put 1 and 4. This is just one of them, possible. You can put any value. For example, if you put V2 is 2, what will happen? Then V1 become 2 times 4, which is 8, isn't it? This is the same. This is the same as if this is 3, what will happen? You will get 12, isn't it? Is it clear or not?
Yep.
Okay, this is the equation of line, so you can put any values. Okay. Up to here, is it clear?
All good, sir.
Good. So now you get the first eigenvector. Okay, and let's use the simplest one, yeah, for 1. It's okay, right? So then you have two eigenvalues a while ago, 6 and 1, right? So now for the eigenvalue 1, what you will do the same thing, yeah? So you will include this. So now become minus 1 and minus 1 here. Okay, and now 4 minus 1 is 4, correct? 2 minus 1 is 1. So now you have 4 V1 plus 4 V2 equals 0. Oh, this must be 1 and minus 1, isn't it? Right? Yeah. So 1 and minus 1. Yeah. This one you can put any. Yeah. So remember, V1 is equal to minus V2, right? Right? The small. So in that case, you can put, for example, this one is equal to, this one is minus 2 and 2. Possible? This one is equal to, this one I can put 3 minus 3 and 3. Possible? Remember, this is an equation of a line, so I can put any number as long as the proportions still the same. Up to here, is it clear or not?
This one is -2 and 2.
Yeah, you can have -2 and 2. That one is okay. Or
Okay.
2 and -2. That's also okay. The same, right?
Oh, okay. But does it have to be the same numbers? Like,
Yeah, should be this one. This is the
oh, okay.
right. Should be the
So
same. Yeah.
that is the constraint.
Yeah, that's exactly the line equation.
Okay,
Should be the
sir.
same number. Okay, based on this. Is it clear or not?
Clear, sir.
Clear, yeah. So you know already how to calculate eigenvalues and eigenvector. You see? Easy? Okay. So now you have two eigenvectors, okay, which are all real numbers. Okay. So in that case, you can look at this. If your eigenvalues are distinct, yeah, if your eigenvalues are distinct means different. Okay. For example, 6 and 1, they are different, isn't it? So if your eigenvalues are distinct, then they are linearly independent. Yeah, the eigenvector are linearly independent. So remember, if they are linearly independent, they can form basis vector, yeah, coordinate system. Oh, so can you still remember basis system, basis vector? Okay. So now, you remember the sum of diagonal entries is called trace. Okay. And the sum of eigenvalues is basically the trace of a matrix. Look at this now. Okay. What is the trace of this matrix? Anyone? What is the trace of this matrix? Hello?
The what trace?
Yes. Trace mean the sum of diagonal entries. So what is the trace of this?
7.
7, yeah?
5.
5 plus 2, okay?
Yep.
So the trace is 7, okay? So what is the eigenvalues? A while ago. Do you remember?
That is
6 and 1, right?
yes.
Okay, what is the sum of the 6 and 1?
7.
Also 7.
Oh,
Ah, now you can see. Okay, so the eigenvalues, okay, the sum of the eigenvalues, okay, is exactly the same of the trace of that matrix. So the trace does not change. Super. Can you see the pattern now? Okay, so the trace of the matrix exactly the same. Yeah, the trace is 7. Eigenvalue is 1. So in that case, the other eigenvalue must be 6. As simple as that. Yeah. If you know one of the eigenvalues, the other eigenvalue you can calculate based on the trace. You don't need to calculate long way to do a quadratic equation or a cubic equation. Okay. Clear or not?
clear.
Okay. So how about the products? Okay. If you multiply the eigenvalues, okay, that will be equal to the determinant of the matrix. Wow, another interesting properties, yeah. So a while ago, the eigenvalues are 6 and 1. Multiply 6 and 1. And then, of course, 6 multiplied by 1 is 6. Can you calculate the determinant of this? Determinant is AD minus BC, right? So this one, 5 times 2 minus 4, yeah. So in that case, 6 also. Yeah, so the determinant of the matrix is exactly the same as the products of eigenvalues. So once you know the eigenvalues, okay, you can multiply all of them, and then it will be exactly the same as determinant.
Sir,
Hey,
can you explain how to get lambda 2, sir?
lambda 2. Lambda
Yes.
2, a while ago we already did. This one.
Oh, so it's from the equation.
From the quadratic equation, from the polynomial
Um,
equation, basically. Okay, you have
okay.
the A, you minus with lambda times I, and
Mm-hmm.
then you take the determinant. That's
Oh,
why, that's why you multiply, you will get back the determinant, of course, because initially you
oh,
get it from there. Right? Initially you get it from there.
okay, sir. Thank you.
Clear, yeah?
Clear, clear.
Yeah, clear, yeah. So you know how to do characteristic equation. So there's a quiz today. Is that correct?
I don't know.
How
Okay.
about this? So is it clear or not? This one? So question first. If you don't get it, I go here. You get more confused.
I don't think there is no quiz, sir.
Oh, there is no quiz today.
Yes.
Oh, okay. Okay. So this is called. We have two eigenvector eigenvalues. Yeah. So one is called right and left. Yeah. So left eigenvector and right eigenvector. So the one that we use usually is the right eigenvector. This is what we usually use. Okay. Why this is called right? Because you see the eigenvector appear on the right of A. Okay. But you can also use left. Yeah. You can use also left. So, but be careful. Left means this must be row vector. Yeah. So, so this must be also row vector. Yeah. So it is also possible to get left eigenvector. Yeah. So, hey, this is another characteristic of distinct eigenvalues. Remember, when your eigenvalues are distinct, do you understand the meaning of distinct? Okay. If they are different, yeah. If lambda I is not the same as lambda j, okay, that means, okay, any two distinct eigenvalues of a matrix, yeah, then the left eigenvector of the eigenvalues is orthogonal to the right eigenvector of the others. So you will see if you use the left and right eigenvectors, and then the right eigenvector is V and the left eigenvector is U transpose, then you can multiply that. And then you will get 0. Yeah, you will get orthogonal. So eigenvectors, okay, of distinct eigenvalues are orthogonal. Okay, so can we practice this? Can you calculate the left and right eigenvectors? And once you do, you can tell me. Share your screen. Put it in the notepad or piece of paper is fine. Yeah, the matrix is simple. Okay. Once you make it, please share your screen.
Sorry, sir. Left and right tadi ya dua itu tuh. Kayak 1 sama 6 itu.
This one, this one. This is the right and this is the left.
Kalau U transpose tuh apa?
This is a row vector like this, and then multiply by a vector equal to lambda times a row vector. Okay, this one is a square matrix multiplied by column vector equal to lambda multiplied by column vector. This one is transpose mean row vector. Yeah, U transpose here is row vector.
Let me give example first, sir.
Okay, let's do the example. Okay, so actually eigenvalues are the same, yeah, both left and right. Yeah, so the eigenvectors, these are the 1 and 4. Okay, and from there you can get the left and right eigenvectors. Okay, exactly the same but different numbers. Yeah. So first you calculate the characteristic equation, okay, and then you create the polynomial equation, and then find the roots. Yeah, exactly the same thing. Okay. So, okay, up to here, is there any question first? So let me go to the books now. Okay, so we are in chapter 7. Okay. I hope you can see. Okay, so we are introducing the characteristic of square matrix. Okay, so matrix usually consists of many scalar elements, right? The question is, can we characterize matrix by a few numbers? Okay, so if you have a square matrix A, can you find a scalar lambda and a vector x so that this equation is satisfied? Yeah. So any solution of this equation is called eigenvector. Yeah, x is eigenvector, and lambda is called eigenvalue. Yeah. So there are many names. Okay, eigenvalue, sometimes we call it proper value, characteristic value, latent value, latent root. Yeah, the same thing. Yeah, eigenvector, sometimes we call it proper vector, characteristic vector, latent vector. Yeah. So you remember A times X equal Y, A represent the linear transformation last time, yeah? So in this case, if A times X equal to lambda X, that means the Y is equal to lambda X. That means what? This is just a scalar multiple, yeah, of X, right? So this is just lengthen or shorten or change direction. Okay, so to calculate that, so you have this equation. Yeah, remember A is a square matrix of order n. That means n by n. Okay, and you put this in the left hand side, so you will have this one, right? And then you put x together, so you will have px equals 0. So p is equal to a minus lambda I a while ago. Yeah. So now you want to solve this. That means the determinant must be 0, right? And then you will get a polynomial equation. Yeah. So in exponent n. Yeah. Sounds like a complicated, but I give you an example a while ago. So 2 by 2. Yeah. 3 by 3, of course, exponent 3, and so on. Is it clear or no? So this is the important part. Okay, so if you have a square matrix order n, then maximum you will have n distinct eigenvalues and the corresponding eigenvector. So remember, eigenvalues are the root of characteristic polynomial. They can be, because this is root of a polynomial, can be complex number or real number. Okay. And then can be repeated. Repeated mean the same values, yeah, not distinct, or actually distinct. Yeah. So if they are repeated, so you ask how many repetition? Yeah. The number of repetition of the eigenvalues is called algebraic multiplicity. Yeah. So when the eigenvalues are all distinct, okay, so then this is called simple. Yeah. There is no multiplicity. So no repetition of eigenvalues. So this is called a simple eigenvalues. Okay. Now a square matrix with simple eigenvalues are diagonalizable. Okay. And then this is the most important part. Yeah? Okay. A square value with simple eigenvalues are diagonalizable and the eigenvector are linearly independent. That means they can become a basis vector. Okay. So if you can find this, okay, you can make it diagonalizable, okay, and then make it into linearly independent. So they can become a coordinate system. Okay. So of course, sometimes in computer, okay, you will create a standard, yeah. So you can create any scalar multiple of x, isn't it? But if you want to make it standard, usually we normalize so that the eigenvector is actually a unit vector. Yeah, that means the inner product is 1. Okay, so I give you example here. So suppose this is A. Okay, what you will do, you create the characteristic equation, right? And then you get the determinant equal to 0. So determinant, you remember AD minus BC, isn't it? Okay, so minus 1, okay, minus 1 minus lambda multiplied by 4 minus lambda, okay, minus 3 times 2, which is 6. Yeah, and then you solve this as a quadratic equation, you will get lambda plus 2, lambda minus 5. That means eigenvalue is minus 2 and 5. Okay, the same thing with this. Yeah. So if you have the same matrix here, and you already know that lambda 1 is 5, lambda 2 is minus 2, then you can calculate the eigenvectors. Yeah. So remember these are example that the eigenvalues are real numbers and distinct. Yeah, separate, you see. 5 and minus 2, they are not the same. So then you will have linearly independence. Yeah. So you can solve this using RREF. You see, I'm solving this using RREF. So I get x1, and for lambda 1 equal to minus 2, I solve using RREF. I get this second vector, yeah, eigenvector. So up to here, is there any question or not? This is another examples only. Taran, is it clear or you are sleepy? Clear or not clear? You want to practice? Do you want to practice or not? Well, this is exactly the same as the slide a while ago. So do you want to practice or we continue?
Yeah, just continue, sorry.
Okay, let's continue in that case. Okay, let's continue. I will continue with the slide. So once you have the eigenvectors, okay, once you have the eigenvectors, you can concatenate the eigenvectors to become a matrix. Okay, so that matrix is called modal matrix. So this is your first eigenvector, second eigenvector, and so on. Okay, and then you concatenate. Yeah, each eigenvector become one column in that matrix. Okay, then it will become modal matrix. Okay, so why this modal matrix is important? Because this is now become the new basis. Okay, so you can multiply by the coordinate, you can get the new coordinate, right? And then this is also useful for diagonalization. That means that matrix A, if I multiply by M inverse and M, I will get new matrix which is diagonal. Okay. From there, of course, I can put it back. So if I know the diagonal matrix, I can multiply with the same modal matrix and the inverse. I will get back the A. Then you ask, what is that for? Ah, yeah, Daphne always asking that. Okay. So here, what is that for? Okay. I'll give you example here first. Okay. So this is your matrix. Yeah. 5, 4, 1, 2. This one will have eigenvector. Remember, a while ago we already computed. Yeah. 4, 1 and 1 minus 1. Okay. So in this case, we form a model matrix. Yeah. See, 4, 1. So I put it here. And then 1 minus 1. So I put it here. Is it clear or not? Model matrix is just concatenate. You see? Is it clear? So once you have this model matrix, then we can create diagonal matrix. Yeah. Remember this only for distinct eigenvalues. Yeah. What will happen? Why we want to make it diagonal matrix? Okay. Because when you have a diagonal matrix, then it will behave like a scalar. Okay. Function, any function, including derivation. How do you get the derivation of A? Second derivation of A. A is a matrix. Okay. Any function. The way to do is find the modal matrix and create the diagonal matrix. And then you apply that function. Example. Okay. If I want to get A exponent to 1.2 or 1.2, how can I call exponent 1.2? If A exponent 2, I can calculate because A times A, right? But A exponent 1.2, you cannot do, isn't it? You can, yeah. How? First, you get the modal matrix, and then you form the diagonal matrix. And then it is the diagonal that you exponent to the x, which is 1.2. But exponent of the diagonal matrix is exactly like scalar. Yeah, like the scalar element. So the exponent to 1.2. Okay, as simple as that. And then you multiply back, you will get this A exponent 1.2. The same thing. If I want to get the exponent, for example, of A, wow, how can I get the exponent of A? So you get the modal matrix, okay, and the inverse, and then you get the diagonal matrix, and then it is the diagonal matrix that you exponent. Okay. The result of this multiplication will become A exponent A. Is it clear or not? I give you example, yeah. So back to this example, okay. So let's find matrix P so that you will get diagonalization. Yeah. So easy, yeah, because you already know the eigenvector of this. Okay, so you get the eigenvector with this 4, 1, and 1 minus 1. From there, you can get the inverse. Okay, these are the inverse of P. Okay, this is actually the modal matrix. Yeah, this is the inverse of modal matrix. And then when you want to get the diagonalization, you just multiply. Yeah, P minus 1 x P inverse multiplied by A, and then multiply by the modal matrix. Yeah, and then you will get diagonal matrix. Oh, look at the diagonal matrix. What is this number? 6 and 1. What is this? The eigenvalues. Yeah, the diagonal is actually the eigenvalues. You see? Interesting, yeah? So, uh,
So A is the initial matrix and B is the
modal matrix.
model.
Correct. A is the initial matrix, yeah? And P is the modal matrix. This is the inverse of the model.
It's how to find the eigenvalues.
Mm, no, it's not how to find eigenvalues get from the characteristic equation.
Yeah,
Okay,
but we can also use this.
this one is to get the diagonal matrix.
Mm.
Okay, so diagonal matrix is this one. So then from here, okay, you can apply. For example, here, oh, I want to exponent d exponent 7. What you will do, you will multiply 7 times, right? Okay, but if you use diagonal matrix, okay, you don't need to calculate like this. All you need to do is d exponent 7 is the same as each element exponent 7. You see? Each element in the diagonal exponent 7. That's it. So if you have diagonal matrix, it will behave like scalar. That's why diagonal is important. Can you get it? So to get diagonal matrix, you need to get the modal matrix and eigenvalues and eigenvector. Can you see the uh, trace of the idea? Do you get the idea or not? For example, this one. Okay, what is the diagonal? I already have the D with this diagonal matrix. I want to get the inverse. How to get the inverse? Easy. Yeah. Oh, inverse is just 1 over. So I will get the result is just 1 over 2, and then this one is minus 1 over 2. As simple as that. Okay. So diagonal matrix will behave like scalar. That's why if you can form a diagonal matrix, then everything becomes simple. It's no longer matrix, it's just scalar. Is this clear or not? The same thing, right? For example, this one, yeah? Or this one, how do you get the A exponent 2.75? Wow, you cannot multiply 2.75, right? But you know the modal matrix. So, okay, so you know the modal matrix, okay, and you know the diagonal. So in that case, any exponent of the diagonal is the same as exponent of the A. Okay, using that, okay, we know, okay, the modal matrix is this one, and the diagonal is this one. So in that case, A exponent 2.75 is the same as modal matrix multiplied by the diagonal exponent 2.75, and then inverse of the modal matrix. Okay, you see here, this is the modal matrix, this is the inverse of modal matrix. The diagonal element is 6 and 1. So all you need to do is 6 exponent to 75, and then 1 exponent to 75. And then multiply the 3 matrix, you will get this. Awesome. it clear, the application? Right? You cannot multiply exponent of 2.75 because, yes, exponent 2, you can multiply a by a, but 2.75, how do you do that? So this is a way to do, okay? First, you make a modal matrix and diagonal matrix. Clear or not?
M is the model, D is the diagonal.
The modal matrix is just eigenvector. You concatenate.
Oh,
Okay?
okay.
As easy as this one is just eigenvector. You see, a while ago, you see a while ago. This one, the eigenvector, you remember? Okay, the eigenvector is this one. See, eigenvector is 4, 1, 1 minus 1. And then you form the modal matrix. It is just
Mhm.
concatenate. Is it or not?
Not easy, but doable.
Yeah, a lot of computation, I understand. But the concept, I hope you understand the concept. Okay. The, the difficulty is to form the characteristic polynomial, right? And then to calculate the root, okay? And then get back the eigenvector. That's mendoksai, a lot of computation. Okay, once you have that, then it's okay. You can get the form modal matrix and you can form diagonal. That's easy. After that, if you want to make it into any function, okay, of the A, that is the same as any function of the diagonal matrix. The modal matrix does not change. See? Why does not change? Because this modal matrix represent the basis. Remember the uh, coordinate system. Okay, and this can only be done if your A have distinct eigenvalues. Okay? Distinct means difference, no repetition. Is it clear or not? So, any question? Is this too fast? Okay. So, once you have that, so you can get the exponent, same thing, yeah? So, if you have the exponent of, you want to get the exponent of A, right? So, then all you need to do is to get the exponent of T. Okay? The same thing. So, if you have the, if you want to get the exponent of T, that means I just reverse this one, yeah? This one going here, this one going to the other side. Okay, so you can get back. Okay, so there is a connection between the diagonal, yeah, and the actual matrix, yeah, as long as you can get the modal matrix. Remember, modal matrix represent the basis. That's why you can do like this. Okay, so with that we can these are the a few characteristics, yeah, that when you calculate the determinants of A times B, yeah, this is true for all matrix. Okay, and determinant of M multiplied by minus M minus 1, this is the modal matrix, should be equal to 1. Yeah? Okay, since we have this one, okay, so then we have the determinant of A is equal to determinant of this value. Okay, but the determinant of this one is 1, so in that case, determinant of A is the same as determinant of T. Okay, so now this is a good news now. You said a while ago that we need to find distinct Okay, and eigenvalues can be complex number. Okay, so can we find something interesting? Yes. If matrix A is real and symmetric, then okay, the eigenvalues are all reals. And not only that, the eigenvector are orthogonal. Okay, so this is called symmetric decomposition. Yeah, if you have any A which is actually symmetric and real number, then you can always find diagonalization. Okay. Okay. So if A is also positive definite, then of course the eigenvalues is not only real but also positive. Yeah? Is there any question? Is it clear or unclear? You tell me.
I think we need to be slow, sir.
You need to be slow. Okay. Let
A lot of
new
I
concept.
think there's new concept.
Okay, so let's come back to the book in that case. Okay. Computation of eigenvalue, eigenvector. Is it possible or not? Okay, clear or not? Or you want to practice so that you will know?
It's clear, this part.
This one is clear. How to get the eigenvalues, eigenvector, is it clear or not? So suppose this is your matrix A. So you form a characteristic equation, and then you will have three roots. Right? So these are the three roots. Okay, they are not distinct. You see there, you have 2 and 2. This is multiple, right? So, and then you have 3 eigenvectors. Yeah, be careful. Even though the eigenvalue are the same, the eigenvector are not the same. Yeah. So now this one, this is the example. Okay, that you have matrix that is not diagonalizable. Yeah. Why? Because this one have repeated eigenvalue of 3 and 3. So they are not distinct. In this case, eigenvector is 1 and 0. Again, this is example that the matrix A are not diagonalizable. So you cannot make diagonal with this. Okay. So when the eigenvalue are all these things, not repeated, then it is diagonalizable. Is this clear or not? So here, example, 2, 4, 5, 3. Okay, the eigenvalues is 7 and minus 2. So this one is not the same. They are distinct. Can you see? So in that case, okay, because the eigenvalue are all these things, they are diagonalizable. So you can find the diagonal matrix. 7 and minus 2. Of course, the diagonal matrix is actually the same as the eigenvalues. Okay. Now, if the matrix A is symmetric, yeah, these are the example of symmetric matrix, right? You see, 2, 2, 3, 3, 4, 4 here, yeah. So then you are sure that the eigenvalues are all real. Can you see? The eigenvalues are all real, not complex number. Okay. And not only that, the eigenvector are always linearly independent. Yeah. If the matrix is symmetric, you are sure, okay, 2 things. Number 1, okay, the eigenvalues are all real numbers. Can be distinct, can be repeated, no problem. But the eigenvector are linearly independent. Now, if all eigenvalue are distinct, yeah, simple, then they are diagonalizable. And not only that, not only linearly independent, they are also orthogonal. Okay? If they are distinct, then the eigenvector are orthogonal. Okay, so this is example. Okay, this is a symmetric matrix, and the eigenvalues are 1, 2, 3, which is distinct. So I can form the modal matrix. Yeah, so I just copy this. Yeah, 3, 0, 8, 0, 4. So 0, 3, 0, 8, 0, 4. And then 0, 7 minus 0, 5, 0, 4. I just copy. Yeah. Okay. And these are the P, which is the modal matrix. And these are the original vector. And then this is the inverse. Yeah. But, you know, this is, because they are distinct, so this is actually orthogonal. What's the meaning of orthogonal? You can just transpose, yeah. Okay, you just transpose, you will get the inverse. Okay, you just transpose, you get the inverse. And then you multiply all of this, you will get diagonal matrix. The diagonal matrix, of course, will be the same as eigenvalue. Is this clear or not? Oh, discussion first. What did you get?
Sir, so let me can I clarify?
Yeah, okay.
So P inverse, this is 0.3066 is the inverse,
Mm-hmm.
and then multiply it by the A, the
Yeah,
initial matrix.
correct.
And then the other P is what, sir?
P is the modal matrix.
The model, oh, P is the model matrix.
Yes.
Meanwhile, minus one is the inverse of it.
Inverse of the modal matrix. But remember,
Inverse
it's
of the
symmetrics. Okay. This asymmetric matrix and the eigenvalue are distinct. That means the
Mm.
P and the P inverse is just transpose.
Oh, okay.
Okay. So in that case, you can get the values. Is this type. Okay. So
Okay.
question, Davin?
Not yet.
Not yet. Can I continue a little bit and then you will present your work? Last part.
Sure, sure.
Okay, this one. This is called Cayley Hamilton equation. So if you know, okay, the polynomial equation like this, yeah, of matrix A, then you can always find function of A as n similar to this polynomial characteristic equation. Okay, you just change the lambda with A. Okay, you will find a function, okay, of function of A, which is the same as equal to 0. So this equation is called Cayley Hamilton equation. So let's give example. Yeah, suppose you have this matrix. Okay, so you calculate the characteristic polynomial, you get this. Okay, so you get this equation. So now all you need to do is you change the lambda with A. So then you will have A squared minus 4A plus 3. So I can get this equation. Yeah. If I know the characteristic equation, the lambda I can change with A. Okay. So you can try. Okay, this one is 1, 0, 2, 3. I square it minus 4 multiplied by this A plus 3 multiplied by I, right? So if you calculate, you will get 0, 0, 0. See? Exact. Okay. So a matrix is called singular, have no inverse if and only if lambda equals 0 is the eigenvalue of A. Okay, so suppose this matrix, okay, you will see the eigenvalues is 0, 5, and minus 3. So because it has 0 eigenvalues, that means that this matrix is singular. It has no inverse. Yeah. So of course, right? Because if you multiply them, it will become determinant. Yeah. So that's the same thing. Yeah. So this one is the Cayley Hamilton-Cayley theorem. Okay. Suppose A is a square matrix of this order, and P is the characteristic polynomial. Then matrix A will satisfy its own matrix polynomial characteristic. PA equals 0. Okay. So suppose this is your matrix. Okay. And then what you will do is you create the characteristic polynomial. So how to do that? You minus with I times I, lambda times I. So 0 minus lambda, this one is in here 2 become 2 minus lambda, 3 in here become 3 minus lambda, isn't it? So, and then you take the determinant of this, yeah? So this is the determinant, and then you simplify, you will get this characteristic equation. Okay? So with that, now you can replace any lambda with A. So minus A exponent 3 plus 5 of A squared minus 8 times A plus 4 times I, that will become 0. Yeah, this equation is called Cayley Hamilton equation. Yeah, so you can create a new equation of A based on the characteristic polynomial, which is equal to 0. Okay. Now, one application of this is to find the matrix inverse. Okay. For example, can you find the matrix inverse of this one? Okay. So you can create the Cayley Hamilton equation.
Sure.
Hey,
How do we get the A cubic R A square?
this one is here.
Itu kita define atau gimana?
No, this one. For example, okay, I will come back. This is A, yeah.
A square-nya bisa jadi gitu.
This is A is okay or not?
Oke.
And then can you get this or not?
Yes.
From here, can you get the third one or not?
Aku pengen yang itu loh, yang A square paling bawah.
Yang paling bawah yang mana? Yang ini.
Bukan, bawahnya lagi.
Ini.
Bawahnya lagi.
Yang ini.
Bawahnya lagi.
Bawahnya lagi.
Ya itu, A kuadrat sama A pangkat 3 itu loh, dari mana?
Ini dah.
Iya.
You multiply A times A.
Oh, nggak bisa satu-satu ya?
No, this is A times A become A square. A times A times A become A third, isn't it?
Ya, 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 ya.
You got it, right?
Ya, ya, ya.
This is A times A. This one is 3 times A times A
Ya,
times
ya,
A.
ya, ya.
Okay? So this is no problem. And then you can form this one.
Ya, understand.
Understand. Okay. And then after that, just to prove that this is actually become 0. Okay. So once you have that, okay, suppose you already have this. Okay. What is the usefulness of this? Of course, I can find matrix inverse. How to do that? I just multiply. So this is the same matrix a while ago. This is the value. Okay. So what I will do is I multiply with matrix inverse, A inverse. So if I multiply by matrix inverse, what I will get? I will get this one, right? So in that case, I will have matrix inverse equal to, wow, I can just do algebra with it. Okay. I can do algebra, which is interesting now. So now I can get the matrix inverse as a squared minus 5a plus 8i multiplied by 1/4. Okay, so this is a simple form of matrix inverse in the form of A. Yeah, Hamilton-Cayley theorem. Okay, is this clear or not? Yeah, the same. This is example. Yeah, this is your A. Yeah, this is simple because 2 by 2, right? So then you create the characteristic polynomial. Okay, how to do? Minus with lambda I. Yeah, in the diagonal. Okay, and then this is a determinant. So AD minus BC. Okay, so you get this characteristic polynomial, and then all the lambda you change into A. Yeah, lambda square become A square. Minus 6 lambda, you got minus 6a. This one minus 4, that means 4i. This one, yeah, 4i. Okay. So, okay. With that, you can, if you multiply by a inverse, okay, a square multiplied by a inverse become a, right? And then 6 of a multiplied by a inverse become I multiplied by a inverse become a inverse. Oh, from there I can you just do algebra. Okay, so you will get a inverse equal to this value. Oh, interesting. Yeah. So you do real algebra here. Is this clear or not? Yeah, these are the same. Another example only. Yeah, just repetition. Okay. From there, you can also do diagonalization a while ago. Yeah. So if you can multiply by the modal matrix, yeah, you can get diagonal. Yeah, you can get the diagonal. Okay. These are the modal matrix P, and this one is the inverse of modal matrix. Okay. If you know the diagonal, you can get the A back. Okay. Remember, modal matrix is just eigenvector, yeah, concatenate of eigenvectors. Okay. So this multiplication like this is called similarity transformation, yeah, meaning the A is similar to diagonal matrix. Okay. So if you can do that, then we can do a lot of function. Okay. So if A is similar to B, so B is, for example, diagonal element. So if A is equal to B, then they will have equal determinant, they will have equal characteristic polynomial, they will have equal eigenvalues, their rank is the same, their trust is the same, their transpose is the same, their inverse is also the same. Okay, their matrix power is the same, the exponent is also the same, and so on. Okay, so this is the application of eigenvalues, eigenvector, yeah, is to create a similar matrix, yeah, with this, if possible, diagonal. Okay, so with that, I hope you get the nice properties of eigenvalues and eigenvector. These are very, very basic understanding of linear algebra. Okay, so these are example, matrix power and exponent. Again, you can use modal matrix to get diagonalization. After you get the diagonalization, now you can form any function of the diagonal and then multiply that with the similarity transformation to get the function of A. Yeah. Okay. So, and symmetric matrix have many applications. For example, covariance matrix is symmetric matrix. Correlation matrix is also symmetric matrix. Distant matrix is also uh, symmetric matrix, isn't it? So what will happen if you do eigenvalues and eigenvector of symmetric matrix? Yeah. One characteristic of symmetric matrix is the transpose is equal to A. Yeah. So with that, this one, yeah. You can, if you can find all eigenvalue of symmetric matrix are distinct, okay, then A can be transformed into diagonal matrix, okay, and they become orthogonal. Yeah. The modal matrix become orthogonal. Orthogonal matrix mean the P transpose equal to P inverse. Yeah. So this is very interesting values. Okay, so with this, the linear algebra is done. So you can present your work. Your group projects.
Who first? Sir.
Okay, ask discussion first. Okay, go.
Ah, who first? Who goes first?
You will go first. Go.
Oh,
Kanto ako sing sa screen rin.
so.
Yes, ka na.
Okay, share your screen.
Iso, Pin. Where are you at now, sir?
In Jakarta. Just
Jakarta.
in front of Bundaran HI.
Oh. You have meet business there?
Yeah.
Okay.
Oh.
Okay, Alexan.
Okay.
Morning, sir and friends. Today we will present our differential project. It's called the visualization of stock market. Next.
Yep.
And what's our project? We will make a clear stock price flow animation, including the buy and sell signal, support and resistance level, and also the prediction accuracy. And what make our project unique? We will try to implement the combination of RSI and MACD indicators to dynamically learn and adjust the parameters based on the prediction accurately. So if it is correct, it will learn and adjust the parameters. And if it's wrong, it will also punish the program and it will try to change the parameters also.
Okay. So there's a feedback system.
Yes. So here are feedback loops. So the word is price changes. The price changes will affect the indicator analysis.
Mhm.
When the analysis is done, it will make a prediction. After the prediction, the program will test.
Mhm.
After this is finished, either it's correct or wrong,
Mhm.
the program will try to dynamic learn and adjust the parameters on the indicators.
Mhm.
And on the next frame, it will be repeated, and make a loop.
Mhm.
Next.
So next, when we're talking about stabilization and equilibrium in this state, in this case, so in our program, the equilibrium is occur when the force acting on the price are balanced with the sorry the when the buying and selling price are balanced.
Okay.
And then for the stability, the stability comes from the supports and resistance in our code. In this case, we have static and dynamic support and resistance.
Mhm.
So the support and resistance will be the levels where the price fluctuates between those levels. However, when the price break through the line, it will calculate the new resistance line and support line because we make it dynamically. So it was adjusted to the price situation.
Okay.
And then we're gonna
Create
show
new
our code.
equilibrium.
What is it?
It will create new equilibrium.
Yep.
Yeah.
Next.
Can
Can
we
you
show
show
our
you
Yeah,
the
you
oh,
can
sorry,
program?
program.
show.
Okay, wait,
Actually,
let
it's not
there.
perfect yet, sir,
No, it's
since the
okay.
accuracy is still low, and we need to find out how to make it better.
Okay, no problem. Can you make it larger so that you can see?
Okay. Can you see it clear?
Yeah.
Or
Yes.
so we make it. There are two types of support and resistance. So we make the static as green color, static support green color, resistance static as purple, and then for the dynamic is the blue and the black line.
Okay.
So it is calculated for in the past 1 year for PPCA. So we used MACD and RSI, and it was adjusted dynamically. So this dynamic is also moving. Is also changing line with the price. So when we
Clear nih.
move it, the yellow one is the trend line. We use the robust regression concept.
Okay.
Clear nih, Vin.
Oh, display. Oke. Ngelek soalnya kalau di replay.
Uh, as you can see, the below the price animation, there is the MACD animation.
Mm-hmm.
That's also to show the buy and sell signal. So when the MACD line, the blue line,
Mm-hmm.
crosses above the signal line, the red line,
Mm-hmm.
it suggests the bullish trend, and vice versa.
Okay. So how do you calculate the new equilibrium?
You mean the support and resistance?
Yes.
Finding the new top and
Bottom.
bottom.
Hmm. In the
But
past, how many months or how many number of days
For what, sir?
to get the new equilibrium? How do you get that? I thought when it breaks, then you create the new equilibrium. No?
The logic I try to implement in the program is when it breaks and it's fulfill some apa ya kayak maksudnya volumenya besar gitu, the volume is big, it's like will make a new equilibrium. If it's just kayak cuma bentar tok dikit gini, it will not make the new equilibrium.
Okay,
So
so it
if
also
it crosses
depends
just a
on the
little bit,
volume.
sorry,
So it's also depends on the volume.
yes.
Okay. And how stable it is?
um I think it's pretty good, I think, but not that not that accurate, but I think it can show the stabilize pretty great. Coba ulang dari awal sih.
yeah, the final accuracy is 41%.
Enggak,
But
bukan. Ini sih buat buat
oh,
resistance support. Coba plain dari awal.
okay, resistance support.
This is pretty big. Uh, the width.
Yes.
Yeah.
As you can see there, wait, pause. Itu yang hijau kan sempat cross the support
Yeah.
line, but the volume is not that big, so
Okay,
it
so
will not make the new.
you ignore.
Yes.
Okay,
Lanjut.
this one also cross.
Yang ini, maybe the program detects the volume is big, so it makes the new one.
In that case, you need to show also the volume so that we can see also,
Hmm.
right? Because that is one of your main factors. So if you plot in the same line, so we will see that volume is actually big or not, right?
Okay.
Anyway, that's just visualization.
Mhm.
So what I see here is your support and resistance level becoming smaller, the width, the bandwidth,
Yes.
yeah, the bandwidth become smaller and smaller, right?
It's also.
Hmm. So over your time, you see the support and resistance, the
Yeah, becomes
bandwidth
smaller and
becomes smaller
smaller.
and smaller. So is this see becomes smaller?
Yes.
Yeah.
Actually, at first we tried to implement your idea, like where the left side is the test,
Mm-hmm.
wait, the sample, and the right side is the test
Correct.
price. But we tried like for 2 weeks and we cannot figure it out. So I think we try to make a new idea, and this is
Okay.
our last project.
It's okay. So this is very good. So that idea you can test next semester in other courses. No?
Okay, sir.
Okay,
Okay.
no problem. So please continue this one so that you can use and reuse for the better and better result next time.
Okay. Okay, sir. Thank you, sir.
So yeah, excellent.
Thank you, sir.
And so
Yes. Oh, the other groups.
Yes, let me share my screen.
Mhm.
I should also tell you the features and what you can do with the code.
Okay.
Wait, let me open the file.
So this is the three courses you combine into one project also, or
Oh,
separate?
no, sir. This is only for difference equation, isn't it?
Oh, okay.
differential
For mine is also for difference equation only, sir.
Oh, okay. How about the
equation.
OR and
The portfolio management and the back testing.
okay.
Should we do the linear algebra and OR presentation in the next
Okay,
lesson?
the next hours. Okay, no problem.
Yes. So again, this is using matplotlib.
Okay.
Uh, this is the settings that I want you to know, sir.
Mm-hmm.
So rabbit lifetime 15, you can actually adjust this. This
Yeah.
is just when one rabbit is spawned, it will live for 15 seconds, and you can adjust uh, with the user's input. This
Okay.
is the fox. This one is carrot lifetime extension. It means that every time a rabbit successfully eats a carrot, it will extend its life by 20 seconds. Again,
Okay,
you
so
can
you can make games.
yes. Fox lifetime. Again, when a fox successfully eats a rabbit, you can adjust the lifetime.
Okay.
And then sensing range. Sensing range is the
Yeah.
ability to detect the
Okay.
entities.
So it's the radius
Yes. The
or
image.
diameter.
Oh yes. Image size is the default.
No problem.
I
Yeah.
will show you later. And the growth rate is just 0.01. You can adjust it as well. Touching range, you can also like put the parameter in what range can it considered to be touch.
Okay.
Let's do a demo.
Okay.
Where's the play button?
Uh-huh.
Oh, is it?
Now,
appearing on the
to
screen?
share the whole screen so that we can see.
Okay, let me share my whole screen. Share screen all. Can you see this, sir?
Mm,
Is it available?
yeah, okay.
Okay, now let's see. Let's just spawn carrot first. Oh, there. Another one there. It will be in random places there.
Okay, no problem.
And then the rabbit there.
Mm-hmm.
This is just a picture I got from Google,
Yeah,
and I implement this. I haven't implemented the
round,
world, yeah, the round world,
round one
but
is easy.
yeah, so it can actually be random,
Mm-hmm.
sir. I still put it
This is
random.
based on grid, like
Yes, sorry.
cellular automata or no?
Yes, this is Cellular Automata. Oh, it crashed.
Okay.
Oh, what happened? Wait,
Okay.
it has error. So basically, sir, the our idea for the next semester,
Mm-hmm.
we will try to make it into a game, sir. So let's say, for example, we will live as a cat, as a rabbit, right, sir?
Mm-hmm.
So our main objective is that we can explore the world
Mm-hmm.
to find carrots,
Mm-hmm.
right? And the carrot will make us bigger. But also, we should avoid fox.
Okay.
So we want to make it a game,
Okay.
so we can control the rabbit, but the fox and the carrot will be autonomous, will
Okay.
be spawned anywhere. Our main objective is to just reach the longest time, or maybe we can make another interactive components, like maybe perhaps the rabbit will find another rabbit and then they can talk with each other,
Yeah,
like
we need.
the normal games we used to play back in
Okay.
the days.
Okay. So I want to see the stability.
The stability.
Yeah. Last time I saw you asked the AI about Volterra APM. Yeah.
Oh
Agent.
yes,
Yeah. So why you did not present that? That's very interesting part.
Volterra. Wait, hold on. Oh, I think I have a lot of terminals. Oh,
So yeah, even though this is a simple model, okay,
mm-hmm.
this is basically predator and prey.
Yes, this one is predator and prey. Can you
And
see?
yeah,
Yes, so it can interact with the rabbit and see the fox will chase it immediately.
I cannot see.
Oh, you cannot see. Oh,
You still okay.
oh, still having an error.
Okay. So
Okay. Yesterday I tried, it was still okay, sir. Hmm.
yes, in one night.
Yeah, yesterday, last night, it was still okay, but then it got the same error again.
Maybe you
Is
show
the
this is the second PY. Maybe you want to show the PY3.
PY3 okay? Yeah. And then I think this one is the right one.
Mhm.
Oh yes, this is the right one. Sorry, I got the wrong codes. So this one is the one. The rabbit will run away as it senses the fox,
Mhm.
and there you will see the fox will eat the rabbit there. I will spawn another rabbit, and there I will spawn another rabbit carrot. But the issue here is it will actually stop when the fox eats a rabbit. So this is a future improvement, sir. So
Mm-hmm.
it successfully eats at least one another ones. It will be
So,
chaotic.
uh, what will happen if no more rabbits?
If there's no more rabbit, then automatically the
King.
carrot will not be eaten, sir.
So, meaning the carrot should grow and
Hmm.
the fox should
Okay.
die,
Okay.
right?
So maybe in the future game, we will develop in the next semester. We should make
Right,
it
right,
bigger,
right.
right?
And the fox should die because of hunger.
The fox would okay. Yes, okay. So we should implement more
Yeah,
concepts
more,
for the next game, yes, sir.
right.
Right. Okay.
And then you want to know
So is
the
it?
stability parameter,
Mm-hmm.
right? So how many fox initially and how many rabbits, so that it will continues forever.
Mm-hmm.
And if below certain values, then the fox will die, the rabbit will die, the world collapse.
Yes.
Only carrot will survive. And then if you also check stability, if the rabbit too much, carrot die, all
Mm-hmm.
carrot, and then the rabbit also die. And then
Oh.
eventually, you see there are a lot of possibility that the world will collapse.
Mm-hmm.
So this is the stability theory that you need to check. What is the boundary?
The boundary. Okay. So that means, like I said in the beginning, the adjustment settings.
Yeah, but that's actually the one that you need to find out. Yeah,
Mm.
that is if you can find the
Okay.
mathematics of that, then
Mm-hmm.
you can easily set the parameter.
So for the next semester, we should still use the agent-based
No
modeling, isn't it,
problem,
sir?
you can use any. Yeah. But do you get the
Okay.
idea?
Yes.
Okay. If the number of rabbit too much compared
Mm-hmm.
to the carrots, the world will
Mm-hmm.
also collapse. Meaning the rabbit eat a lot of carrot, no more carrot. The carrot no more, the rabbit also die. This part you
Mm.
did not implement.
Ah, okay.
Right? And then
Okay,
the
okay.
same thing, yeah.
Right, right.
So if the fox is too much more than the rabbits, okay, and
Mm.
then uh, rabbit no more, then the fox will also die. See, the word
Ah, okay.
collapse.
Okay, sir.
So this part you did not implement. So
So
correct,
the dynamics using the Lotka and Volterra model.
correct.
Okay. Uh,
So that
so
will
what do
get
you?
the feedback, no? This one will
Yes.
get the feedback because this is just one eating the others,
Mm-hmm.
just one side. But I want to see
Mm-hmm.
the feedback loop, the one that you show in the causal loop a while ago. Actually, the
Mm-hmm.
other part you did not.
Oh, I missed that part. Okay. But what do you think, sir, for the game that we can
Yeah.
develop next
So
semester?
you can develop any of this, no problem.
Mm-hmm.
Okay. So keep
Well,
continue.
we
Mm.
will make it more like various, sir. So as you can see, this is very
Mm.
normal
So
background.
you can improve not only in what is it, Matplotlib. So you can make it in mobile,
Mm-hmm.
or you can make it in web,
Mm-hmm.
and or in any
Right. So we will make a game, yes, sir, and the
right.
background will be various. We can
Yeah,
see the rivers and the mountains, for example.
no problem. You can
Okay.
visualize
Right.
accordingly.
Okay. Thank you,
Okay.
sir.
Okay.
Thank you for the feedback, sir.
Okay. So thank you very much for today, and I hope you and thank you for the semester. Can you give me feedback for the whole semester of the linear algebra and the half semester of the difference equation, probably?
For me, linear algebra has a lot of new, what
Concept.
is it, concepts, sir, and new what is it, like matrix, the one that we just learned previously,
Properties, nah? So a lot of
properties.
properties. Yeah.
Yes, very. We perhaps we may have difficulties in distinguish them.
Okay. So first you need to read. Okay.
Mhm.
After sometimes uh, you practice a lot, then you can understand this. Okay. Once you understand the properties, then you can use. Okay. It's very difficult to apply unless you understand the properties. Okay. So at least you know first. Okay. After that, you can repeat. Yes, Devon, you want to say something? Yeah. Any other feedback? Darren?
All good, sir.
Huh? All good, Ria?
Um, Mungkin materinya yang kebanyakan atau gimana, tapi kadang itu kayak lompat it's it's meeting
Something.
itu sometimes tuh kayak, "Hah, kemarin kayak pelajaran ini terus kok pelajaran hari ini kok beda banget gitu."
Actually, still the same concept with this say difference equation. Okay. Last week I mentioned already that there is a one special case of CA, okay, which is the same as difference equation, but you use discrete values and space. So then you can use that. In fact, okay, using the CA, you can do a lot. Okay. Compared to difference equation, CA you can start to see the visualization in 2D or 3D. Okay. And you start to create a multi-agent system. Actually, that's the application. Okay. It is in the grid system. So anyway, I'm not sure if you are interested in stock market to apply in CA. I don't know yet. Okay, so maybe you can use, but at least the concept of stability theory, yeah, the concept of equilibrium you can use. Okay. Not everything you will use, that's fine, but I hope this is useful for you in the future. Yeah. So, any other feedback, Daphne? You want to say something? Or Devon?
No, no, sir.
No, sir, just new insights about linear algebra.
Okay.
Oh yeah, anyway, when should we submit the final paper for linear algebra and OR, sir?
I think it's already in Lantera, is it? No?
Yeah, I thought it should be yesterday night.
Yeah, but you requested to be postponed,
Postponed a bit, yeah. Yeah.
right? Last time. So,
Okay.
Yes, maybe, sir, can you make it the same with difference equation, which is next week,
okay, no problem.
Maximum 12, yeah, sir.
Yeah.
maximum 12?
How about
Okay.
our answer, our final term?
The final is already in Lantera, so
It will be open
from
all
morning until evening.
and how many?
The coverage is everything.
Let's discuss the attempts, sir. The
The
attempts,
attempts, you want
Yeah.
2 attempts?
uh,
2 attempts or 1 attempt?
So let's make it two.
Okay, two is
Sure.
fine.
For OR, you said it at 9 till 12.
Yes, from morning to up evening.
No, no, 9 a.m. to 12 in the afternoon.
I don't think so. Hmm. Well, I think I put it all the same.
Difference equation.
Can you check in Lantera?
Yep, I open it.
And
wait, let me refresh.
Which one?
OR, sir, OR.
R.
OR,
Okay.
19th of December, 9 a.m. till 12 p.m. It's it.
OR. Final exam. Oh, this is final report. Final exam.
Differential also.
This one, final exam.
Mm-mm.
Let me
Right.
check the value, the
That
timing.
shall
No. Oh, yeah, from 9 to... Okay, what time you want? From 6 to 10.
10 in the night. Yeah,
Yeah,
okay.
okay. So I will put it until 11.
Yeah. Differential also, sir.
Okay, no problem.
Yeah. Okay, thank you.
I changed this already, the OR.
Okay.
Okay, and then what else do you want? Difference equation.
Yep.
Difference equation. Final exam. December 13. Okay, so you want from 6 to 22:59. Is it okay?
Yeah.
Okay, can you check?
Difference equation. Final. Okay.
So
It's
3
done.
hours. Okay, but if you start from 10 o'clock, you will not get 3 hours, okay?
10 p.m. Yep.
Yeah, so this is 150 minutes, but if you are late, it will not get what you want.
Yep. 6 a.m. until 11 in the night. Okay.
Yeah, but don't get it too late.
Yep, sir. I will not do it in the night.
Okay. So how about the linear algebra? No problem.
No problem. It's
Okay. So
already okay.
okay, so everything is fine.
Yeah.
Good.
Difference equation.
Okay. So the linear algebra. I think this is already from 6 to, okay, I will make it until 10. And then what else do you want?
No, sir. Just
The paper.
the paper.
Paper is for difference equation.
Differential equation paper.
You just put in the projects.
Yeah. And a code.
Okay. And that one is 12 already. And in linear algebra, the projects is also 12, I guess. Let me check. Oh, okay. So this one is 12. Linear algebra is also 12.
Yeah.
Okay. And then what's the other one? OR. You want OR also 12. Are you sure?
Maximum at 12
Yeah,
lah.
maximum. December 12. Okay, so this one OR is also 12. Okay, I will put it 12. 12, 23. Okay, so done. So no more?
No more, sir. That's it.
Okay, so see you in next hour. We'll discuss about IFN.
Okay.
Okay. Yeah, see
Okay,
you.
okay.
Thank you.
See you. Bye.
Know that this is still, but from the what is it, sir? From the idea, I think it give me like a lot of possibilities of where this program can go, especially if we
Yeah,
learn
that's good. So
AI
at
and
this
software.
point, I just want to see the stability and sustainability of the system.
Mm,
Okay.
mm,
So you need to make a possibility that the rabbit will die, okay, because of hunger. The fox will die because of hunger. That part you
mm.
make yet
Oh, okay, okay. Hunger.
hunger. Because
Actually, in uh-huh.
if no more rabbit, the fox will die because of hunger.
Yes.
You
Actually,
can
I
make
think
that.
in the code I already make the settings. So if it fails to catch another rabbit, it will
After
die.
certain times.
Yes, it after certain times. I, that's why I make the. Can I show you the code again? So this one is the here's the so actually here you can see here that I make the time rabbit lifetime is 15. This is, but in this part I said carrot lifetime extension. So if it fails to get the carrot, it will
Mm,
die in 15
mm,
seconds. It's also the fox responsibility to find the rabbit answer.
yeah,
If the
to get
fox
the rabbit.
is if the fox manage to find the rabbit, it will extend only by 20 seconds. But if it fails, then it will die.
Mm,
So I think there's a small error in the animation for this one.
okay.
I will we will make sure that in the next semester this one will be like a game already, so we
Okay.
can
Okay.
controlling one rabbit only, sir. Because
Okay.
like
So if it is a game, so you ask other people we are not familiar with programming to play so that
mm,
you can test
right.
can and then you can get their input and feedback.
I think in Python is do you like know a way, sir, to control like
You can use
Q W A S
TV,
D
yeah, TV.
the keyboard, I think, yes, sir.
Yes.
To make it move forward is to click W, I think, yeah.
No, you can use Kiwi.
Okay. Oh, yeah. I heard about that.
Yeah. Yeah.
Kiwi. Yes, yes.
Okay.
So, so actually, what give me idea, sir, between all of us.
Mm-hmm.
There used to be this game, sir. In back in the old days, I think you know. Do
Mm-hmm.
you know the fishing game, sir? The called Feeding Frenzy, sir. Do you know?
Okay. So.
So basically, it's a game where different levels, of course. But we can control one unique fish.
Mm-hmm.
So it and then a random entity will spawn, sir.
I
A
see.
random entity like what is it, like another bigger fish, and then the biggest fish also.
Mm.
So we must survive, and the goal of the game is actually to eat as much fish until the bar is already full.
Okay. I played that last time. Yeah.
Yes, so that is the idea, sir, for our next semester's game development, sir. I think it's very interesting, sir.
Okay. So uh, let's discuss it along the way.
Okay, sure. Next semester, isn't it, sir?
Before the next semester, that's fine also during the holiday.
Oh yeah. I actually opened a net logo
Okay.
previously,
Good.
sir.
Good.
I see a lot of potential, sir,
Okay.
uh, in the code. So perhaps I will be familiar with a lot of programming language like net logo
Good.
and then Python and then even Scratch, sir.
Okay.
Scratch.
So that
Yeah,
is also nice,
yes.
even though
So
this is for children. Yeah.
yeah, I know. So a lot of possibilities, sir. This
Great.
is, I think, we are moving towards the game, yes, sir, for different
No
equation going
problem.
to the
Okay. So if
software
you like
engineering.
that, that's okay.
Yes.
Okay.
Okay.
Okay. Thank you.
So, uh,
So see you in the next hour.
yes,
Okay.
it's very weird, sir. Not like usually we go eats together. Aneh, sir, rasanya wis di rumah kabeh iki.